This is benzene. It might look harmless, but long-term exposure can damage your bone marrow, reduce your red blood cell count, suppress your immune system, and even cause cancer. However, benzene is found everywhere in our modern society, in pharmaceuticals, plastics and polymers, petrol, explosives, dyes, and detergents, just to name a few. Here's a molecule of aspirin, with the benzene ring right there in the middle. This is ibuprofen, paracetamol, polystyrene, TNT, serotonin, dopamine. The list goes on and on. I even have it in my logo. Fortunately, when we substitute other groups onto the benzene ring, its properties change drastically. You're not going to get cancer from taking aspirin as far as anyone knows. In fact, according to Wikipedia, aspirin may reduce the overall risk of both getting cancer and dying from cancer. So benzene is clearly a very important molecule, but where did it come from? Benzene has a fascinating history that goes back 200 years. It's a story that's closely linked to the development of chemistry from its very early days into the unstoppable force that it is today. Benzene was discovered in 1825 at the Royal Institute in London. I couldn't resist going there myself to learn more about where it came from. Benzene was first isolated by one of the most famous and successful scientists of all time, Michael Faraday. In his honor, the Royal Institute has paintings and sculptures of him all around the building, and rightly so. They also have his original lab, beautifully preserved exactly how it was during the 1800s. You may have heard of Faraday before. He founded the field of electromagnetism. He invented precursors to the electric motor and to the dynamo. He also invented a precursor to the modern Bunsen burner. He was the first person to liquefy gases such as chlorine and ammonia. He popularized the terms anode, cathode, electrode, and ion. In fact, Faraday was so amazing that Albert Einstein himself kept a picture of Faraday on his study wall. So, on top of all of this amazing work, how did Faraday manage to discover one of the most important molecules of all time? Well, in 1825, Faraday published a paper in the Philosophical Transactions of the Royal Society, the world's oldest and longest-running scientific journal, as it's still in print today. This particular issue of the journal contains some, interesting research. Faraday's paper was called On New Compounds of Carbon and Hydrogen and on Certain Other Products Obtained During the Decomposition of Oil by Heat. At the time, in pre-Victorian England, an exciting new technology was lighting the streets with oil lamps. Faraday investigated a fluid obtained during the compression of oil gas. After a load of meticulous distilling, purifying, and testing, he managed to obtain a pure substance that he called bicarbonate of hydrogen. The name bicarbonate of hydrogen came from Faraday's elemental analysis of this new substance, where he discovered a ratio between carbon and hydrogen of 2:1. But hold on, you might be thinking, benzene has a 1:1 ratio between carbon and hydrogen, doesn't it? It certainly does, so let's take a closer look at how Faraday came to that conclusion. These were the early days of chemistry. There were none of the modern analytical techniques that we have available now. Check out my videos on some of those if you want to see how it would be done today. Instead, all Faraday could do was wet chemistry, meaning he could perform reactions and note down his observations. For instance, he was able to determine the absence of oxygen by the inaction of potassium. To determine the amount of carbon and hydrogen in the substance, he passed the vapor over heated oxide of copper. 0.776 grains, which is just a unit for mass, of the substance produced 5.6 cubic inches of carbonic acid gas, which is just carbon dioxide, and 0.58 grains of water were collected. This was equivalent to 0.711704 grains of carbon by calculation and to 0.064444 of hydrogen. He then found the ratio between these masses to be 11.44:1. With our modern knowledge of benzene having a 1:1 ratio between carbon and hydrogen, this ratio of almost 12:1 makes sense when we consider the relative masses of each element. Underneath, Faraday says that these quantities nearly equal in weight the weight of the substance used, and making the hydrogen 1, the carbon is not far removed from 12 or 2 proportionals. In other words, he was saying that there was a 2:1 ratio between carbon and hydrogen in the substance. Remember, this was a time when the concept of the atom had only been around for a couple of decades. Back then, they thought the relative mass of carbon was closer to 6 rather than 12, which led to this incorrect ratio, hence the original name of bicarbonate of hydrogen, suggesting 2 carbons for every hydrogen. Over the next few decades, more work on atomic theory led to the discovery of carbon's true relative atomic mass, so the correct ratio between carbon and hydrogen in benzene was soon rectified. By the way, I double-checked this calculation right here, and it seems to be a mistake on Faraday's part. If you divide this number by this number to find the ratio, it actually comes out to 11.044, not 11.44. I must have put this into my calculator around 20 times just to be sure. When I went to the Royal Institute, I told them about this, and they told me that although Faraday was a genius when it came to physics and chemistry, his math skills were slightly lacking, and he tended to make mistakes. This new substance Faraday had isolated was extremely interesting to scientists at the time. It was highly unsaturated, meaning it contained an unusually low proportion of hydrogen in comparison to carbon, which caused it to burn with a particularly smoky flame. By this point, it was well known that unsaturated hydrocarbons undergo addition reactions. However, Faraday's new substance was unusually resistant to addition reactions, which didn't make any sense considering just how extremely unsaturated it was. This was a time when scientists didn't yet have an understanding of bonding or structure, so it was difficult to explain these observations. One of the many things Faraday was able to determine was that upon combusting this new substance, 1 volume of vapor requires 7.5 volumes of oxygen for its combustion. 6 of the latter combine with carbon to form 6 of carbonic acid, and the remaining 1.5 combine with hydrogen to form water. Knowing what we know now about benzene, these ratios make perfect sense when you consider the balanced equation of its complete combustion. He goes on to say, the hydrogen present therefore in this compound is equivalent to 3 volumes. This essentially gave Faraday a formula of C6H3, which supported his name bicarbonate of hydrogen. However, if we take a closer look at these numbers, the 1.5 equivalents of oxygen that combined with hydrogen to form water actually indicates an equivalent of 3 waters that were produced, not of 3 equivalents of hydrogen in benzene. And because water has the formula of H2O, the formation of 3 equivalents of water is actually evidence that benzene contains 6 equivalents of hydrogen, giving us a formula of C6H6. I'm not sure if this was another mistake or if it was due to the limitations of scientific understanding at the time. It was known by this point that water had the formula H2O, so in theory, the correct ratios in benzene could have been worked out from these observations. I'm not trying to downplay Faraday's work here. He was undoubtedly a genius, one of the all-time greats. There's a reason Einstein had so much respect for him. Faraday couldn't have known just how impactful this discovery would be on the future of society. Amazingly, at the Royal Institute, they still have Faraday's very first isolated sample on display there, with a handwritten label reading bicarbonate of hydrogen on the vial. Faraday's discovery sparked a surge of research into this fascinating new substance. In 1833, a German chemist called Eilhard Mitscherlich managed to synthesize it by distilling it from benzoic acid, which was extracted from gum benzoin, a substance that had been used in perfumes and medicine for centuries. He gave the compound the name benzene, which later became benzene. In 1836, the French chemist Auguste Laurent, who synthesized many derivatives of benzene, named benzene fen, which eventually became the root of the English word phenol and phenyl. But what about the structure of benzene? Today, we take the concept of valency for granted. This is the idea that certain atoms can make a specific number of bonds to other atoms. However, when Faraday first isolated benzene, the concept of valency hadn't been discovered yet. That all changed in the mid-1800s, thanks to the chemist who today is perhaps the most strongly associated with benzene, more so even than Faraday. The chemist I'm referring to is, of course, Auguste Kekulé. In 1857, Kekulé published work where he established the valencies, or number of bonds formed, for different elements. 1 for hydrogen, 2 for oxygen, 3 for nitrogen, and 4 for carbon. Using these rules, he was able to correctly establish how atoms bonded in different molecules. Just a few months after this, Kekulé published more work where he described the ability of carbon atoms to link to each other. Now this was groundbreaking stuff. Kekulé had laid the foundations for the theory of chemical structure, particularly when it came to carbon, and this soon exploded into the field of organic chemistry. But Kekulé was just getting started. He turned his attention towards benzene and tried to use his revolutionary ideas to determine its structure. This troubled Kekulé for years, but in 1865 he finally published a description of a structure for benzene consisting of 6 carbon atoms in a ring with 6 hydrogen atoms surrounding them. He also described how the carbons would be connected by alternating single and double bonds. Now, let's take a look at that famous Kekulé structure for benzene as he depicted it for the very first time. Here it is. Not what you were expecting? Yeah, me neither. So let's see if we can decipher this. The guide at the top is the key. Chaîne ouverte depicts an open chain and chaîne fermée depicts a closed chain, with arrows at the ends to show how the molecule connects to itself in a ring. So Kekulé's benzene is depicted here as a closed ring. The different atoms are depicted with different shapes. Atoms with higher valencies, or in other words, atoms that can form more bonds, are drawn as longer lines. So the carbon atoms are 4 times longer than the hydrogen atoms because carbon can form 4 bonds, whereas hydrogen hydrogen can only form one. A vertical overlap depicts bonding between atoms. Remember, this was before the electron had even been discovered, so the true nature of bonds was something of a mystery. For example, this carbon is making a single bond to the carbon underneath it, a single bond to the hydrogen underneath it, and its remaining two bonds are to the next carbon underneath it, showing a double bond. So this all gives us the classic Kekulé structure that we're a lot more familiar with today, with its alternating single and double bonds. We can also see Kekulé structures for all of these substituted benzenes, which contain various branches, as well as other atoms like chlorines, oxygens, and nitrogens, all with their correct valencies. We can see chlorobenzene, phenol, aniline, and toluene, just to name a few. This was incredible work from Kekulé, especially when you consider just how little he had to work with at the time. Around this period, other chemists also proposed possible structures for benzene. One such chemist was James Dewar, who now has this amazing plaque at the Royal Institute. He's also known for his invention of the vacuum flask, his original designs of which are on display there. In 1869, he published work that described what bonded molecules might look like. He demonstrated this with a device that had brass circles representing carbon atoms connected to brass bars representing the carbon's bonds. Again, nobody was quite sure what the bonds between atoms actually were since the electron hadn't been discovered yet. Dewar showed different configurations for 6 carbons, including one for benzene with 6 latent affinities or carbon-hydrogen bonds. This structure is very similar to Kekulé's structure, except for the fact that it only contains 2 double bonds and there's a bond going across the middle of the ring. Dewar benzene was eventually synthesized in 1962. Someone else who proposed a possible structure for benzene was Adolf Karl Ludwig Claus, a German chemist who suggested a hexagonal ring where each carbon was also bonded to the carbon opposite. Modern simulations and calculations have shown that synthesis of Claus's benzene is impossible due to the enormous amounts of strain it would exhibit. Another German chemist who proposed a structure was Albert Ladenburg, who worked with Kekulé and suggested a prismatic structure. This structure, now known as prismane, was eventually synthesized in 1973. Most of these possible structures explained why only one isomer of monosubstituted benzene could ever be found. However, there was still a big issue for Kekulé: disubstituted benzenes. If Kekulé's original structure was correct, there should always be 2 isomers for a 1,2 disubstituted benzene, one where the groups are separated by a single bond and one where they're separated by a double bond. This would mean there should be a total of 4 isomers for any disubstituted benzene. However, chemists could only ever produce 3 isomers. One isomer was always missing. So, in 1872, Kekulé published an update for his ring structure where he added that there must be 2 possible structures for benzene that are in equilibrium with each other. By rapidly alternating between the 2 structures, the 2 1,2 disubstituted isomers would be indistinguishable. More evidence would come later on to confirm Kekulé's ring structure once and for all, but with slight tweaks to the nature of the bonding. Towards the end of his life, in 1890, Kekulé was asked to speak in front of the German Chemical Society for a celebratory lecture of his lifetime achievements. Here, for the first time, he told the story of how the idea for chemical structure, including the structure of benzene, first came to him years earlier. Here's an 1897 translation of Kekulé's own words from that lecture, describing his journey home across London, where he was living at the time, from his friend's house in Islington to his own in Clapham. One fine summer evening I was returning by the last omnibus, outside as usual, through the deserted streets of the metropolis, which are at other times so full of life. I fell into a reverie, and lo, the atoms were gambolling before my eyes. Whenever hitherto these diminutive beings had appeared to me, they had always been in motion, but up to that time I had never been able to discern the nature of their motion. Now, however, I saw how frequently 2 smaller atoms united to form a pair, how a larger one embraced 2 smaller ones, how still larger ones kept hold of 3 or even 4 of the smaller, whilst the whole kept whirling in a giddy dance. I saw how the larger ones formed a chain, dragging the smaller ones after them, but only at the ends of the chain. I saw what our past master, Kopp, my highly honoured teacher and friend, has depicted with such charm in his Molecular Welt, but I saw it long before him. The cry of the conductor, Clapham Road, awakened me from my dreaming, but I spent a part of the night in putting on paper at least sketches of these dream forms. This was the origin of the structure theory. Later in the lecture, Kekulé described another dream he had had years later when he was professor of chemistry at Ghent University in Belgium. I was sitting, writing at my textbook, but the work did not progress. My thoughts were elsewhere. I turned my chair to the fire and dozed. Again, the atoms were gambling before my eyes. This time, the smaller groups kept modestly in the background. My mental eye, rendered more acute by repeated visions of the kind, could now distinguish larger structures of manifold conformation. Long rows, sometimes more closely fitted together, all twining and twisting in snake-like motion. But look, what was that? One of the snakes had seized hold of its own tail, and the form whirled mockingly before my eyes. As if by a flash of lightning I awoke, and this time also I spent the rest of the night in working out the consequences of the hypothesis. Somehow, over the years, this story has morphed into Kekulé seeing an actual image of a snake eating its own tail, also known as an Ouroboros, but according to this 1897 translation at least, he never explicitly claimed that at all. Now, in reality, considering Kekulé only revealed the story of these dreams 25 years after he first proposed the ring structure of benzene, it could be something he made up to add some magic to the discovery. Or maybe the idea really did come to him in a dream. Either way, Kekulé came up with a great model for the structure of benzene. However, it still wasn't perfect. One glaring problem was that if benzene did have a load of double bonds, it should be very good at addition reactions, just like any other unsaturated hydrocarbon. However, as I mentioned earlier, it was unusually resistant to addition reactions. The chemical test for a double bond is to see if the substance decolorizes bromine water, but benzene has no effect on bromine water. In fact, chemists observed that benzene tended to do substitution reactions rather than addition reactions. Another problem chemists observed was to do with the enthalpy of hydrogenation for benzene. When reducing cyclohexene to cyclohexane, chemists were able to measure an enthalpy of hydrogenation of minus 120 kilojoules per mole. With 1,3-cyclohexadiene, there's a second double bond to hydrogenate, so it was expected the enthalpy would be roughly double, and it was pretty close at minus 232. With 1,3,5-cyclohexatriene, aka the Kekulé structure for benzene, we'd expect the enthalpy to be roughly triple at around minus 360, but in reality it was much less at minus 208 kilojoules per mole, indicating benzene is a lot more stable than it should be. In 1929, developments in X-ray crystallography allowed benzene's shape to be confirmed once and for all. A brilliant young scientist named Kathleen Lonsdale used X-ray diffraction to prove definitively that the atoms in benzene were arranged in a flat hexagonal plane, just like how they're arranged in graphite. This was an incredible achievement considering it was done in a time when all of the calculations had to be done by hand. In her paper, Lonsdale said that her reasoning supplies a definite proof from an X-ray point of view that the chemist's conception of the benzene ring is a true representation of the facts. In other words, the hexagonal ring structure had been confirmed. Sorry, Prismane. She also determined that the carbon-carbon bond lengths in the benzene ring were around 1.42 angstroms, or 0.142 nanometers. This confirmed that the bonds weren't alternating single and double bonds like they would have been in the Kekulé structure, because if they were, benzene would have alternating long and short bonds. As a result of her amazing work in the field of crystallography, Lonsdale was one of the first women to be elected a Fellow of the Royal Society. She was the first woman tenured professor at University College London, the first woman president of the International Union of Crystallography, and the first woman president of the British Association for the Advancement of Science. Today, University College London has a science building named after her, which, after some refurbishments in 2018, was reopened by none other than Sir David Attenborough. Now, by the time Lonsdale had published her findings on benzene, there was a new kid on the block in the world of science: quantum theory. Many scientists, including Einstein and Schrödinger, had used some ridiculous maths to figure out the shapes of atomic orbitals. These are the regions around the atomic nucleus where you're likely to find electrons. This helps scientists to determine the true nature of bonding between atoms. Thanks to all of this work, we're finally getting close to our modern understanding of the bonding in benzene. In 1931, just 2 years after Lonsdale's landmark publication, a German chemist called Erich Huckel applied the recently established molecular orbital theory to benzene, which allowed him to calculate how the orbitals were arranged in the molecule. Huckel emphasized the importance of delocalized electrons in the conjugated system of benzene, which contributed to its unusual stability. In 1933, American chemist Linus Pauling, now famous for the Pauling electronegativity scale, explained why benzene was more stable than the Kekulé structure indicated. He said that benzene has an average resonance energy between the two Kekulé structures. In other words, he suggested that the true structure of benzene was an average between each of the two possible Kekulé structures, and that this average was more stable than each of the extremes. Now we can put all of this together to look at the true structure of benzene as we understand it today. To understand it properly, we need to first look at the bonding in a simpler molecule. This is ethene. It's another unsaturated hydrocarbon with just one carbon-carbon double bond. 3 of the carbon atom's 4 outer electrons are located in molecular orbitals called sp2 hybridized orbitals. For now, don't worry too much about the names or the reasoning behind this, but these orbitals are observed whenever a carbon atom is surrounded by 3 other atoms. The carbon-carbon sigma bond in the molecule is the result of the 2 carbon sp2 orbitals overlapping with each other, and the carbon-hydrogen sigma bonds are due to the hydrogen's s orbitals overlapping with the carbon's sp2 orbitals, giving us bonds that are all oriented 120 degrees from each other. Both carbon atoms also have an electron in a p orbital that sticks out above and below the plane of the molecule. These p orbitals overlap side-on to result in a pi bond, which has electron density both above and below the plane of the molecule. Now, according to Kekulé, benzene was similar to ethene in that it also contained double bonds. However, here's where Kekulé was wrong. Rather than the carbon p orbitals overlapping to give us 3 separate pi bonds, they instead all overlap together to give us a continuous, delocalized pi system, with electron density both above and below the plane of the ring. This means that these carbon p electrons are free to move around the whole ring, so rather than being localized between 2 carbon atoms, they're delocalized. This explains everything. It explains why benzene doesn't undergo addition reactions like any other alkene, because it's not an alkene. It doesn't have normal double bonds. It has a delocalized pi system. This is why we observe substitution reactions. It explains why only 3 isomers of disubstituted benzene could ever be found. It explains why benzene is more stable than it should be due to Pauling's resonance energy, where benzene is a more stable average of the 2 extreme Kekulé structures. Rather than double bonds alternating their positions around the ring like Kekulé thought, the electrons are delocalized around the ring. It explains the shape of benzene due to the arrangement of the orbitals. At last, a mystery that persisted for over a century was finally solved. Benzene and molecules like it are now called aromatic, indicating a delocalized pi system that gives rise to these interesting properties. This story is a beautiful example of how science can lead to changes in our understanding over time as more evidence is discovered. Who knows what we'll discover next? I'll leave you with a quote from Kekulé from that famous 1890 lecture. "Let us learn to dream, then perhaps we shall find the truth." If you enjoyed this video and would like to support the channel, please consider liking and subscribing, and let me know in the comments if you have any questions.